welcome to my individual project video presentation on paper aeroplanes and dynamical systems. We will first be focusing on introducing an additional force to our system of thrust to more accurately model powered aircraft such as commercial airliners and fighter jets. In the group project, we investigated this model here, which looked at how our angle theta, the plane's angle of attack or angle in base horizontal, and its speed change throughout the flight. So to add thrust, we simply just add a thrust expression T to our second equation. The only problem with this model is if our aircraft is capable of producing a certain amount of thrust, then our aircraft could gain altitude indefinitely, which is not very realistic to everyday aircraft. So we will then model our thrust and altitude as decreasing exponentially as we gain altitude. It's important that our thrust decreases at a larger rate than our air density so that we still avoid this issue, which then brings a third variable into our system, y being altitude. So then we can introduce a third formula to our system. So with our updated system with lift term, gravity components, drag term, and our expression for our thrust, we can then move this to the corner and analyse the flight with d is equal to 1. So the variables fluctuate a lot in the first few seconds of the flight. It then continues to gain altitude until it gets enough altitude where thrust starts to decrease, so it cannot produce any more lift, which then causes it to plateau. Because its thrust is so low, it then doesn't produce enough lift, then it drops in altitude again, then thrust increases and it increases lift again, and eventually the aeroplane starts to fluctuate and settle to an equilibrium, which we can see as these parameters become constant. When we plot the flight trajectory, it then corresponds to our aircraft having a flat and stable flight. It's important to note that this model does ignore a lot of the complexities with the aerodynamics and atmospheric models, but there is a more accurate model in the GitHub if you want to check that out. So with our parameters, S being greater than 0, theta being periodic, and y being any real number, our altitude, it makes more sense to show these parameters with a cylindrical basis. So we can plot our flight in a phase cylinder. As you can see, our marker, it settles to a constant point at the end there, which corresponds to our aircraft finding an equilibrium state in its flight. Phase cylinders are a good way of representing because it gives a representation of the entire system throughout the flight and what the value of each parameter is at that equilibrium position. It also gives a representation of whether our parameters oscillate. So next I wanted to investigate how our aircraft would behave at supersonic speeds and what its behaviour is like at the supersonic speeds and whether we actually have a stable flight. So we can update our previous model using Accurate's theory, which models increased drag and decreased lift efficiency, and I inputted pilot trim alpha, which is a pilot inputted elevation to our rear stabilisers, which would be more representative of the real world. Then our coefficient of drag becomes a function of speed, where as our aircraft speed increases, it then approaches a drag to lift ratio at the supersonic speed. Denote that as d super, which is 2 in these simulations. When we then plot our speed and flight trajectory, we can see that speed increases very quickly, given the very high thrust we're inputting into the system. However, altitude does not gain very quickly, which reflects our decreased lift efficiency at these higher speeds. So you can see there's a trade-off between speed and lift efficiency. However, the more important thing is whether we have a stable flight. So using the theory of linearization, we can calculate a Jacobian matrix, and essentially if all the eigenvalues of this Jacobian matrix are negative, then we have a stable flight, meaning that if our plane is pushed slightly off axis by a gust of wind, for example, then it will naturally want to return to equilibrium, so suggesting a negative feedback response to these perturbations in the parameters. As you can see, we have these negative eigenvalues, which it makes sense intuitively as our angle theta remains constant throughout our supersonic period of the flight. And through trial and error, we find that with alpha equals roughly 0.012, we have a stable flight and an equilibrium position as found. So now, looking at all that, we can now review what we've looked at and how we've updated these models. So we started with our original system that we analysed in the group project. We then introduced thrust, and drag and how they decreased with altitude. Then we looked for the existence of an equilibrium and the behaviour of our plane as it approaches its equilibrium, what that means qualitatively in a flight of an aeroplane. We then represented these parameters on a graph and how the equilibriums can be represented in a graph and phase cylinder. Then we introduced supersonic flight using Acharet's theorem, which we then found that our plane still achieves stable flight during supersonic speeds by calculating the eigenvalues of the Jacobian matrix. We then found that an equilibrium does still exist when alpha is about 0.012. Overall though, this model is much more applicable and accurate for powered aircraft. So this model has become a lot more general. We've taken our model from an unpowered aircraft to now being powered aircraft, and we can model it at various speeds, both sub and supersonic. So I hope you've enjoyed, and thank you very much for watching.